ABNO is a sterically unhindered and stable nitroxyl radical. It is effective in catalyzing the oxidation of alcohols in air at room temperature. It is most commonly encountered as a replacement for the more commonly known TEMPO, which is another stable nitroxyl radical, but hindered. Since ABNO is an unhindered nitroxyl radical, it is more effective in oxidizing both primary and secondary alcohols. Currently, ABNO is still quite expensive commercially, due to the difficulty in synthesizing it. But in recent years, methods have popped up that synthesize ABNO in a much more achievable and economical way. Stable radicals are pretty cool, so let's try it out. To get started, I set up a stir plate and put an ice bath on top. I put in a 500ml 3-neck flask with a large stir bar. Then to the middle neck, I have attached an adapter with a small dropping funnel. To the left neck, I attach a thermometer adapter to keep an eye on the internal temperature. This reaction should be kept between 4 and 8 degrees Celsius to prevent side products from forming. Now through the open neck, I add in 50 ml of deionized water as a solvent. Then I add in 12.9 ml of benzylamine as the first reagent. Then to the dropping funnel, I add 43 ml of 18% sulfuric acid. Now I dropwise add the sulfuric acid while keeping the temperature between 4 and 8 C. During the addition, the solution turns milky, but it became clear again towards the end. When the addition is complete, I add in 25.8 ml of 50% glutaraldehyde as the second reagent. Then I attach a funnel and gradually add in 20 grams of acetone dicarboxylic acid as the third reagent, while maintaining the reaction temperature around 5 C to prevent decomposition. The solution has become yellow and I stopper the open neck. Now to the dropping funnel, I add in 47.8 ml of a 9% sodium acetate solution. I dropwise add the solution to the flask, which will work as a buffer to stabilize the pH, and then leave it to stir. The full reaction is relatively complex, but the three reagents eventually form a cyclooctane ring containing a ketone with a nitrogen benzyl bridge in the middle, while also releasing CO2 and water. When the addition is complete, it looks pretty much the same, and I remove the ice bath. I then leave the mixture to stir at room temperature for a day to allow the reaction to complete. When that is done, the mixture has turned a piss yellow, and I continue with the next step. So I add 10 ml of 18% sulfuric acid to the dropping funnel. I add it dropwise to adjust the pH of the solution to around 2. This will make sure that the amine of the product is protonated and stays in the water layer. When that is done, it looks the same, and I move it all to a separatory funnel. I then add 80 ml of MTBE and extract the water layer to remove some organic impurities. I repeat the process 3 times and discard the organic phases afterward. I then move the water phase to a 1 liter flask and add 500 ml of N-heptane. I then add 20 grams of silica gel, which will hold on to any solid impurities. I then gradually add 80 ml of a 20% sodium bicarbonate solution to adjust the pH to 8. This causes the amine of the product to deprotonate and move into the heptane. I then take the mixture and filter it all through a glass-fitted filter with vacuum filtration. I then wash the residue with 320 ml of heptane and discard the residue which contains silica gel and some impurities. I then move the filtrate, which contains 2 layers, to a separatory funnel and separate the layers. I take the organic layer, which I have put into one of my broken flasks, and dry it with some sodium sulfate. I then filter the mixture to remove the sodium sulfate and distill over all of the solvent with short path vacuum distillation. When it has distilled to dryness, a white solid is left behind. Now I dissolve the solid in 100 ml of methanol and it turns orange. I clean the sides of the flask with some more methanol and then distill over all of the methanol. When all of the methanol has distilled over, a yellow-orange solid is left behind. I then redissolved all of it in about 100 ml of methanol to give a red solution of the product. Now I set the flask on a stir plate and added a thermometer and adapter. I open the right neck and gradually add in 3.3 grams of sodium borohydride, which turns the solution yellow. The sodium borohydride will simply reduce the ketone to an alcohol. I leave it to stir for an hour at room temperature and it has become a clear yellow. Now I quench the reaction by adding 20 ml of 10% hydrochloric acid, which will destroy any remaining sodium borohydride. I then set the mixture up for short path vacuum distillation to concentrate it to somewhere between 25 and 50 ml. Afterward, I am left with a light yellow solution and some solid that has precipitated out. Now to this mixture, I add 80 ml of MTBE and stir it. I then add 12.5 ml of a 20% sodium hydroxide solution to adjust the pH to 11 to 12. This will cause the product to deprotonate again and move into the organic phase. I move the mixture to a separatory funnel and separate the layers. I then return the water layer to the separatory funnel and extract it twice with 80 ml of MTBE. I combine the extracts with the organic layer and then return it to the separatory funnel. I then wash it with 80 ml of a 4% sodium bicarbonate solution, which will take out some salts and impurities, while keeping the water phase basic to prevent the product from moving into the water layer. I then separate the layers again, take the organic layer and set it up for short path vacuum distillation to remove all of the solvent. Afterward, I am left with a thick orange solid, which should contain the product. Then for the next reaction, I add in 50 ml of 70% sulfuric acid and heat it to 100 C. I loosen it with a spatula to get it to stir and make everything dissolve. Afterward, I add 50 ml more of the 70% sulfuric acid and stopper the flask. I then leave it to stir for a day. This reaction is a simple dehydration reaction, where the hydroxyl group will protonate and leave as water, causing the formation of a double bond. When I come back, the mixture has turned black and the reaction should be finished. Now I set up a large beaker with a thermometer and add in 250 ml of water. Then I add 50 grams of sodium hydroxide and dissolve it to make a 20% sodium hydroxide solution. I then set the solution in an ice bath to cool it down. Then I hover a dropping funnel above the beaker and add in all of the black mixture. Then dropwise I add it to the sodium hydroxide solution. I make sure that the temperature is at or below 30 C to prevent any degradation. I occasionally add more sodium hydroxide solution to keep the pH basic to destroy all the sulfuric acid and keep the product deprotonated and in suspension. When all of the black mixture has been added, it is finished and the resulting mixture has a basic pH. I then move all of the mixture to a separatory funnel in portions and extract it with about 800 ml of ethyl acetate in total. The ethyl acetate is also washed once with water, and then I combined all the ethyl acetate extracts in a large bottle. I dry it with a bunch of sodium sulfate. I then filter it all through some cotton into a 1 liter flask. I then distill over all of the ethyl acetate with short path vacuum distillation, and afterward I am left with a red oil, which should be the dehydrated product. Now for the next reaction, to this oil I add 25 ml of isopropyl alcohol as a solvent. I then attach a two-way gas adapter to perform a hydrogenation. The right connection leads to a vacuum pump, while to the upper connection, a balloon filled with gas can be attached. I first remove all of the air by opening the way to the vacuum pump, and then close it again, which leaves a vacuum in the flask. I then open the way to a balloon filled with CO2, which rushes into the flask. Since CO2 is basically unreactive in this case, it will prevent the catalyst from potentially igniting the solvent when it is added. I repeat this process 3 times and then remove the adapter. I quickly clean the neck with a paper towel to remove the grease, to prevent some of the catalyst from getting stuck there. I then add 1 gram of 20% palladium hydroxide on carbon as the hydrogenation catalyst, which is the whole bottle. I then reattach the adapter and attach a balloon filled with hydrogen to the upper connection. I repeated the same process as before, but with hydrogen, which fills the flask with hydrogen and starts the hydrogenation process. I heat the flask to 45 C and I make sure to stir it strongly to knock the hydrogen into the liquid and increase contact with the catalyst. Since I can't be completely sure how fast and how much hydrogen the reaction consumes, I leave it to react for 2 days and occasionally repeat the pumping and hydrogen filling process. In the reaction, hydrogen and the reagent will attach to the surface of the palladium catalyst. This favorable energy state will allow hydrogen to react with the reagent and remove both the double bond and the benzyl group to form the desired product and toluene. After 2 days, it should be finished and I remove the hydrogen and replace it with CO2. Now I filter the mixture through a glass filter and wash it with more isopropyl alcohol, but still some carbon particles come through, so I refilter it through some cotton and sea light. Since it was really slow, I changed the flask and attached the gas adapter to pull a vacuum and pull it through faster. I also washed it again with more isopropyl alcohol, and the filtrate came out as a clear yellow solution. Since the solution was red before the hydrogenation, it is a good sign that something has happened. I then set the filtrate up for short path vacuum distillation to remove most of the isopropyl alcohol. Afterward, I am left with a concentrated solution of the product, which also contains some toluene. Now for the final reaction, I add 0.8 grams of sodium tungstate dihydrate as a catalyst. I start stirring and the solution has darkened slightly. I then add 25 ml of water to dissolve the catalyst. Then to the middle neck, I have added an adapter with a small dropping funnel. Now to produce the final radical product, I will use the urea hydrogen peroxide adduct, which allows for controlled release of hydrogen peroxide and the formation of the radical product. It comes in these little 1 gram tablets, of which I dissolved 8 in 25 ml of water, and I add that to the dropping funnel. The dissolution of this adduct is endothermic, so the solution is actually at 0 C, which is handy since it has to be cold. Now to start the reaction, I dropwise add the solution to the flask. Gradually the solution in the flask turns darker, and eventually becomes red. When the addition is complete, I add a bit more of the urea hydrogen peroxide adduct to make sure it all reacts. I then leave it to stir for an hour. In the reaction, the sodium tungstate will catalyze the reaction between the amine and the hydrogen peroxide, causing the formation of the nitroxyl radical. When that is done, I move it all to a separatory funnel and extract it 3 times with 50 ml of DCM. We can see the red product moving into the DCM layer. Now I have combined all of the DCM extracts and we are left with a red solution. I then attach a short path distillation apparatus and concentrate the solution. I then move the concentrated solution to a separatory funnel and wash it twice with 25 ml of water to remove remaining urea. I then extract the water layer once with 50 ml of DCM to take out any product that might have moved into the water layer. Now I take the combined organic layers and concentrate it with short path vacuum distillation. When very little of the solution is left, I add 50 ml of heptane, which will help in azeotropically removing all the DCM. I continue the distillation. When only a little is left, some solid has already precipitated out, and I stop the distillation. I then take the flask and move it to the freezer and leave it at -25 C for a day to crystallize out more solid. When I come back, I take it out the freezer and it seems more solid has crystallized out. I quickly filter the mixture through a glass-fitted funnel and collect the solid. I wash the flask once with some heptane and then take the solid residue and put it in a new flask. After scraping out as much as I could, I recovered 1.27 grams of a wet ABNO. Now to remove any remaining solvent, I set it in a heating mantle, heat it to 30 C and pull a vacuum. This will pull out any remaining solvent. We see the solid lightens in color quickly because of the evaporating solvent. And after this, I am left with 0.99 grams of an orange solid. If we assume the purity of this product is 100%, then the total yield calculated from the first step is only 5.74%, compared to 51% from the literature. The part where it seemed to lose the most yield was the first step, since the acetone dicarboxylic acid decarboxylates very easily, which might have had an effect. It is also difficult to know the quality of my starting material, and I'm not sure if I trust the certificate of analysis from Sigma, since the testing date was 3 years ago, which means it has been sitting in storage for quite a while. Also, I haven't been watching the pH of the solutions too well, which is important to know and adjust, so that all the product moves into the correct layer. If the pH of a solution in one of the steps was not right, it could cause a huge loss of product. If I had an NMR, I could test the product after each step, but at least the procedure turned out to work, even without me being able to check the reaction progress. Now since the powdered version is a bit boring, I want to make some crystals. The product sublimes easily, and it also has a smell reminiscent of sweaty locker room and dirty socks. This is actually a handy property, because that means it can be purified through vacuum sublimation. So I set up a Schlank flask and pour in all of the powder. I then attach a cold finger condenser, which is just a stick with cold water running through. I secure it with a small clip and connect the gas adapter to a vacuum pump. I then submerge the bottom part of the flask in a water bath that I heated to 40 C. I pull a vacuum on the flask, and in combination with the heat, it will cause the solid to slowly transfer into the gas phase, without becoming a liquid. When the ABNO sublimes into a gas, it will get pulled upward along the cold finger. Since the cold finger is, well, cold, it will deposit onto the cold finger and collect there. The cold finger is also too cold for the ABNO to easily sublime again, and thus it will stay there. We slowly see the formation of crystal deposits on the cold finger, and after a few hours, it has formed beautiful shiny red crystals. Unfortunately, the layer is too thick to fit through the joint, so the bottom part fell off, but it stayed in one chunk, and I could take it out by grabbing it and making it smaller with some tweezers. I scraped off the rest of the crystals with a spatula, and put them all in a vial. In the meantime, I run the remaining stuff again in the background. Anyhow, I now have some beautiful red crystals of pure ABNO. In this run, I recovered 0.66 grams of the ABNO crystals. I'm happy that it worked, and perhaps I will use it in a future video if I ever need to oxidize an alcohol. Anyhow, that was it for this video. Here's the cost analysis. Pause it to see it. Thanks for watching, and as always a special thanks to my RotoVap support group on Patreon. See you next year.